Okay. So non-determinism we have seen in the previous class. Okay. Now the formal definition of a non-deterministic finite automata is one which can be in several states at once. That means several states can be current states. As we discussed in the previous class, in a non-deterministic automata, you don't just follow one path, which is basically your depth first search, but rather you do breadth first search because you have several possible paths. Okay, and at least one of them, if they take you to an accepting state for a given string, then the string is accepted. Okay, so basically, in the worst case, you might have to explore all possible paths. Okay, so here there is a certain amount of non-determinism regarding how much time will be taken or what is the next step or next transition you should do. So that is why it's called a non-deterministic finite automata. There might be several outgoing edges from from a particular given state on a particular input character. Okay, so you have seen this example also in the last class, and all these definitions we have seen. So this is the formal definition. Only here, please note that the transition function is slightly different from a deterministic finite automata. In case of deterministic finite automata, the mapping is to a single state. Okay, the delta is basically a mapping. I hope all of you realize that a function is nothing but a mapping. You remember that? A function can be defined in the form of a mapping. Okay, so this delta is nothing but a mapping from one state to another on a particular given character, input character. So in case of DFA, this is to exactly one state. In case of NFA, it is to a set of states, not just a single state. So that is the only difference. Otherwise, it's exactly the same 5 tuple. And the transition function, you can also extend it. There could be several paths, and at least one of them should take you to an accepting state. And so that is the language of the finite automata. All those strings which are accepted because there exists a sequence of valid transitions from the initial state to some accepting state or final state. Okay, now today let's look at another type of non-deterministic finite automata, which are called NFA'S with epsilon transitions. Now, what is an epsilon? I have used this term before. Any of you remember? Yes, empty string, right? A string in which you do not have any input character. Okay, so an empty string is typically represented by epsilon. So epsilon transitions. Now we have NFA'S with epsilon transition. So what does this mean? You can say this adds another level of non-determinism to NFA'S if you have epsilon transitions. So what it means is sometimes you have state-to-state transitions on epsilon input. Without consuming any input, you can go from one state to another if such a transition is defined. Okay, and these transitions are done spontaneously without looking at the input string. But it is optional. Please remember, you may or may not make that transition. So again, non-determinism, you have options. Okay. Now let's first see what these are, and then we will see why they might be necessary. So this is an example of an NFA with epsilon transitions. Often these are called epsilon NFA. Okay. So here you can see that you have at least 3 transitions defined on epsilon. So 1, 2, 3. Okay. And so what do these transitions mean? So when you are, for example, in state B here, you might decide to take this transition and go directly to the final state. Okay, so this transition we are taking to go directly to the final state. So in effect, you can observe that this makes this state B, it makes this state B a final state. Okay, because these are linked by an epsilon transition, without consuming any further input, you can go from state B to state D. You do not need an input to go from B to D. So if you are in B, effectively it means this B is also a final state. Okay. Now, then again, if you are in state E here, then without making any without consuming any input, you might go to state B or state C. Okay, so even though there is no outgoing transition from E on say input 1, okay, so you have got the input 1 next, but you don't have an outgoing transition from E on input 1. Instead, you have an outgoing transition which takes you to C, and from C on consuming this input 1, you could go to D. Okay, so this transition is also possible. So sometimes you have these epsilon transitions defined. You may or may not take them. So you can see that you have previously on a particular input, you had more than one transition defined on the same on a particular input character. Say all of these are defined on one. Now you might also have some epsilon transitions which also are adding to the number of options available to you. So it is another level of non-determinism. Okay, so you can have multiple outgoing arcs on the same input character, or you might have epsilon transitions. So any epsilon transitions in your finite automata will make it a non-deterministic finite automata, because you have the option. You might make the transition without consuming input, or you might stay in the same state. Okay, so epsilon transitions, when you have epsilon transitions, your transition function or the tables, the transition table will look like this here. Okay, phi here refers to the null state, null set. Okay, so I hope all of you can understand the difference between a null set and epsilon. What is epsilon? Epsilon is an empty string. And what is a null set? One which does not have any elements in it. Okay, suppose you have a state like the one which I'm drawing here. Okay, so this is now a set given to me. Is this a null set? Can I say that this is phi?
No, ma'am.
No, ma'am. Because it still has a string. It is the string which is empty, but the set is not empty. Okay, so please be very clear on these distinctions. Okay, so and since these terminologies and these symbols and these conventions will be using again and again in the rest of the course, both myself and Shubhrajit sir. So you should understand these conventions very clearly from day one. Okay, it's not day one, but still as soon as possible. So epsilon is an empty string. In C, for example, you might represent it with two double quotes like this, and phi represents the empty set. Okay, so this is very clear. So that means from B on input 0, there is no outgoing transition defined at all. Okay, so that is why this is phi. But on epsilon input, okay, this is no input at all actually, there is a transition which can take you to D. Okay, so it is possible, here it is not possible, in this NFA it is not possible, that from B, when you have an input character 0, you might wish to check out whether D has an outgoing transition on 0 or not. In that case, you might still make this epsilon transition to D, and then if D has an outgoing transition on 0, you could make that. Okay, so this is the extended transition table for an NFA with epsilon transitions. Okay, so you have seen an example. Let's see what we can do about this. Now here we have, yes, any doubt?
Yes, ma'am. Ma'am, in case in case in a small sigma transition state diagram, we do not have any
It's not
transition.
sigma, it's epsilon.
Sorry,
Two different characters.
epsilon. In an epsilon transition diagram, in case there are no like multiple final states or like multiple transition states, would it make it a would it make it a deterministic finite state machine, or would
No. Any even a single epsilon transition makes it non-deterministic. So epsilon, so there are two conditions basically which can make a finite automata non-deterministic. One is presence of multiple outgoing arcs from any state on any input character. Okay, even if just for one state there are more than one outgoing arcs for the same input character, then it is an NFA. Okay, the rest of it might be very deterministic, but even that single condition, it can make it a non-deterministic finite automata. And even the presence of a single epsilon transition will make it a non-deterministic finite automata. Okay, because you have a choice. Please remember, please note. Okay, you might make that epsilon transition or you might not without consuming any input. Okay, you might decide to stay in the same state and check out the outgoing transitions from this very same state, or you might decide to make a epsilon transition. Okay, by the way, this is epsilon. I'm just writing it down so that you can pronounce it properly. It is epsilon. Okay, and it represents an empty string. Okay, so now let's come to a new concept, which is epsilon closure. What do you understand by epsilon closure? And epsilon closure is defined with respect to states. For every state, you can define an epsilon closure. And epsilon closure consists of the set of states you can reach from a state Q following only arcs labeled epsilon. Okay, so from any state, if you follow only the arcs which are labeled epsilon, what are the states you can go to? Okay, so if you look at the examples, it will make it perfectly clear. This is the same epsilon NFA from the previous slide. Okay, so first let's look at epsilon closure A, which is the start state. Okay, there is no outgoing arc explicitly defined on epsilon. Okay, so epsilon closure A consists of only A. You can always stay in A without consuming any input. Okay, so it is as if there is an implicit arc here on epsilon. Okay, so this is implicit, even if it is not given explicitly. Epsilon closure A consists of the same state. Without consuming any input, you stay there. Now let's look at B, state B here. Okay, so epsilon closure B consists of B, first of all, for the same reason as before, and also because there's an outgoing arc on to D. Okay, so without consuming any input, you can go to D. So D is also included in epsilon closure B. Okay, similarly, now if we look at epsilon closure E, okay, from E, of course, E has to be there, but you can see there are two outgoing epsilon arcs. Okay, one takes you to B and the other takes you to C. So B and C are included. Now, the moment you include B, you can see that B also has an outgoing epsilon arc. Okay, so and which can take you to D. So that means when I am in E, without consuming any input character from the input string, I can land up in state D following this epsilon path. Okay, so D also is included in epsilon closure B. Is that clear? Okay, so all those states to which you can go from a given state without consuming any input, that means by following epsilon paths, okay, they are part of the epsilon closure of that state. So for every state in the finite automata, we can define an epsilon closure like this. Is this clear now? Can all of you understand what is epsilon closure?
Yes, ma'am.
Okay, so this is a very important concept. You must understand how we are going to behave when we are working through a finite automata. If without consuming any input, there is a set of states which are available to us, it is our present state. It is as if our present state is not just a single state, but a set of states. I am currently, when I am in E, actually, I am not only in E, but I could at the same time be in B, C, and also D. Because without consuming any input, I can make a next transition from any of these states. So it is as if my current state is not just a single state as shown here, but this entire subset of states is my current state when I'm moving through the NFA. Okay, so this is an important concept which we'll be using subsequently. Okay, now extended delta. Now remember transition function. The transition function on epsilon, extended delta on epsilon. Now we are extending the idea of delta again. So if you make a transition on epsilon, you basically go to epsilon closure. This actually you can call it the definition of epsilon closure. Okay, it is not just epsilon closure, it's actually the definition of epsilon closure. All those states that I can go to without using any input character. Okay, so the induction proof is there. I think you can do it. So it is the set of all states you can reach from Q following a path labeled W. Here it is not W, it is epsilon. Okay. And the language of the NFA. Now NFA, we have already seen the language of the NFA is all those strings which can be accepted. Okay, that means it's not necessary that every path you follow should take you to a final state, but if there exists a path that you could follow to land up in a accepting state, then that string is accepted. And in case of epsilon NFA, that means NFA with epsilon transitions, okay, you have to follow this extended delta. That means you have to also take into account these epsilon transitions. This is slightly complicated. Let's not go into this. Let's see how we can make we can convert this epsilon NFA into a normal NFA. Okay, because it is when you are writing a checker, epsilon NFAs are difficult to handle. So let's see how we can define the equivalence of NFA and epsilon NFA. Now, what is meant by equivalence? I'm sure you have studied the equivalence relations, partitions of sets, etc. In discrete maths. Have you studied it? Do you understand what is meant by an equivalence relation?
Yes, ma'am.
Yes, ma'am.
How will you define it? Can you define it, any of you?
It is symmetric, transitive,
And
And?
reflexive.
Reflexive.
Symmetric or antisymmetric?
and antisymmetric, transitive, and reflexive.
Yes. Okay. So basically equivalence means they have to be the same. Okay. So let's keep it simple. In layman's terms, equivalence means they have to be the same. So what it means is for any epsilon NFA, there exists an NFA which is exactly the same. How do you say when do you say that two finite automata are the same? When they accept the same language. So that means for a given NFA, you can always create an epsilon NFA. You could add some epsilon transitions by extending some years. That is a trivial part. But what is important for us is, given an epsilon NFA, we can convert it to an NFA without epsilon transitions. Okay. So for every NFA, there is an epsilon NFA. And the converse is also true. So any equivalence relation, when you have to prove, it is like that if and only if relation. You have to prove it both ways, that this is equal to that and that is equal to this. Okay. So an NFA can be converted to an epsilon NFA. Basically, NFA is a superset as per definition. Okay. All epsilon NFAs are NFAs. And an epsilon NFA, when given an epsilon NFA, we can convert it to an NFA without epsilon transitions also. Okay. So how do we do that? Now, so for this picture should help you to understand. Suppose you are in this state here at this point. So this is your current state, say state A. And there are these several states which are part of your epsilon closure. Okay, so this yellow triangle, it basically represents the epsilon closure. That means these are all the states where you can be without consuming any input. Okay, and then from there you can take a transition on input character A, and you land up in these states on making a transition on input character A. And then subsequently there is another epsilon closure for this state which can take you to several different states. Okay, so these are all transitions on these are all epsilon part of the epsilon closure of these particular states. Okay, so these triangles basically represent the epsilon closure of the state at its apex, if you think of it of the leftmost point as the apex. Okay, so if this is the situation, then it means that from A you should have a transition to every state at this point. Okay, so all these states here on A. Is that clear? Can you understand that this is what it means? So that means from this state A, you can make a transition directly on A, on input character A, to any of these states which are coming at this point. Okay, so this is how we are going to remove those epsilon transitions from NFA. Let's see how. So start with an NFA, with an epsilon NFA with states Q, input, start state, final state, transition function. So this is the formal definition of an epsilon NFA. So you have been given an epsilon NFA, and you have to construct or convert it to an NFA without epsilon transitions. Okay, so construct an ordinary NFA with the states Q, input alphabet is the same. Please note one thing, even in the converted NFA, the set of states, they remain the same. The set of states, they are the same. Okay, the set of states do not change. Input alphabet, of course, does not change because we are going to be accepting the same language. Okay, so this input strings will be the same. So input alphabet also has to be the same. The set of states don't change. The start state also does not change, but the final states will change. And of course, a new transition function you are going to define where there will be no epsilon transitions. Okay, so final states, I will come to this later. So let's see what is happening. So basically what you are going to do is you are going to replace the destination by the epsilon closure of that destination. Okay, so from A, when you go to E on 0, okay, so from A you go to E on 0, and then so let's see what is happening here. This column here, note that it is remaining exactly the same. Can you see the column has stayed the same? For this particular input 0, it has stayed the same. For input 1 now, because from E you had transitions on epsilon to B and C, okay, and note that the epsilon closure of B also contains D. So basically you are now going to C and D also, okay, because C remains the same from before. C remains the same here, and from instead of B you are also going to D on input 1. Okay, so this part of the column remains the same, and this part of this particular part, it has entered into this column because you can take an epsilon transition and accept input 1 also. Okay, now I think this will become a little more clear. We'll come to the final states later. This will become a little more clear if we draw the new finite automata that results. Okay, please note the same states. So I have left the space here so that I can draw it. So this is A now. This is B. This is E, C, F and D. Okay, we'll come to what are the final states a little later. So from A, you have the same outgoing transitions. This is on 1 and this is on 0. Please tell me if I'm making a mistake. From B, you have an outgoing transition on 1 to C. So this remains the same as before. From C, you have an outgoing transition on 1 to D. Okay. From D, you have no outgoing transitions. Previously also, it was not, there were no outgoing transitions. This was the final state. And from E, you have outgoing transition on 0 to F. This was there as before. And outgoing transition to C and D on 1. So C and D on 1. This was not there, but because you had these epsilon transitions and you could accept 1 by following these epsilon transitions. Okay, so that is why you now have these epsilon transitions to C and D on 1. Okay, and from F you go to D on 0. This is also same as before. Now for the final states. I'll go back to the previous slide and we'll see how we define the final states. The set of states Q such that epsilon closure consists a state of F. Okay, so all those states. Now basically before trying to convert it to an epsilon NFA, you have to list down the epsilon closure of every state. And for all those states in whose epsilon closure you find one of the original final states appearing. So in this case, this was the original NFA. The final state was D. And we know that D appears in the epsilon closure of these two states, B and E. You can see that is why these epsilon closures are given. Closure for B has B and D. Closure for E has B, C, D, E. So D, which was the original final state, appears in the closure of B and E. So these two states also now have to be made final states, because it means previously also if you were in B, then you could go to D without consuming any input. And if you were in E, you would go to D without consuming any input. So that means you could accept that string. Okay. So that is why in the new finite automata, the one which you are creating without epsilon transitions, along with D, B and E also have to be made final states. Okay. So that is the reason why these stars have come for B and E also. So now we have three final states, B, D and E. Okay.
Ma'am, could you just repeat why E is going to C and D in the revised, like in the NFA version of the epsilon NFA, like
epsilon NFA. See, E is, if you are in this, okay, let's take the original NFA. Here, if you are in state E and you see which input character are you interested in? 0 is clear, right? 0 goes to F. But why do we make a transition on 1? Suppose we are in E and we see 1 in the input stream. Okay, then what would we do? See, we have the choice. We could take this particular, okay, let me, we could take this particular input transition. Can you see my pen? This particular input transition and then take this input transition to D. Okay, or even for C. Okay, suppose we are in C, we want to go to C. We could, for example, follow this path and make a transition on 1. So there were two options for E, the state E on input 1. There were without seeing any input character, you could go to B and C, and both B and C, note that B and C, they have C and D as the destination for 1, right? So epsilon transition to B and 1 transition to C. This was possible from E, okay, following the path E, B, C. So that is why C has to now appear in the destination for 1. Previously, this was not a single arc, but 2 arcs. One from B to E, the other from E to B and B to C. Similarly, there was another possibility that if you go follow the epsilon arc to C, and because D appears in the destination for 1 from C, so you could take this path, 2 arcs, E to C and C to D, right? Is this clear now? So from E, on seeing the input character 1, you could go to C and then consume the character and land up in D. So basically what it means is that from the state E, by consuming input character 1, you could have two possible next states. One was C following this path, the other was D following this path. Okay, so C and D could be your destination states. So they are appearing directly here. Yes.
Ma'am, why doesn't that set have B2 in when we are in state E for the regular
Yes.
NFA, then
Yes.
when we consume 1, we also go to state B, then that
How
set
will you
should
go
have
to
B.
state B and consume 1, please?
When we have 1, we go to state B, then we go to D, but I think that set should have B, C, and D, not just C and D.
Why it will go to B? I am not able to understand how by consuming 1 you can go to B.
From E,
Which path? Which path
from
will you
E,
follow?
the epsilon path.
Epsilon does not consume the input, na?
Oh.
Why don't you understand that? If you have to see, these arcs mean that input character is consumed, and epsilon arc means the input character is not consumed. But if you follow an epsilon path and there is only one path in which the input is consumed, okay, so here these epsilon paths here are basically E to B to C. This consumes 1 here. So this is a two-step path in which the input is consumed in only 1 arc. Now this path, instead of being this two-step, it could be a multi-step path like this. And maybe on only one of them you are consuming the input. That is also possible. Okay.
Hello, ma'am.
Yes.
Ma'am, can
Yes,
we go
please.
to A? Can we go to A to D by consuming 1?
A to D. How will you go to A
Yes.
from E?
A to D and then B to D directly.
Excuse me for a minute. Class nichi. Shubhajit, class nichi. Okay. Yes. Now, what was your doubt? Please tell me again.
Ma'am, I was saying that we can go to A to D via consuming 1 by following
A
the
to
path A
D.
to B. Then
Yes.
Yes, ma'am.
You cannot go from A to D. You can go from A to B by consuming one. You do not take the epsilon paths which come after the character. See, actually Shubhrajit sir has given me a good clue. See, whenever you think of a string, say a string on a particular character, say a string on character 1, you should think of that string as preceded by as many number of epsilon characters as you like. Okay, not following the input character. Epsilons which follow the input character are not accepted, because once you have consumed that input, you are already in that destination state. So your doubt is actually a very good one. I am very glad that you are thinking in this point. So this helps me to clarify this point. So whenever you are thinking of an input character for finding out which is the next transition, you think of that input character. Say if it is an input A, okay, think of it as preceded by epsilon, not just one, it could be multiple epsilons, but not followed by epsilon. If you think of this input character as preceded by as many epsilons as you like, including 0 epsilons, then the states which you have to go to will become very clear. Is this clear now? So let's do one thing. Let's just go back to the diagram which we had seen. Okay, you remember that diagram with triangles? Yes. So here this arc is actually not correct. I'm very glad that you pointed this out. So this helps us to clarify. This arc is not correct. What we are going to put in the NFA are arcs to all these states. So any epsilon paths which come here, this is our epsilon closure. So all these epsilon paths which come here are acceptable. And then finally you consume the input character given and you land in all these states. So when we are creating the NFA, we will put an arc from A to all of these states which come here. These states. So think of these input character streams as epsilon strings, epsilon star. Actually, the star means this star you will learn in detail when you do regular expression. This means 0 or more occurrences. You can have as many occurrences as you like. Okay, so you can have 0 epsilons or you can have infinite number of epsilons. So this could be technically an infinite long path. Okay, followed by the input character A. Okay, so all of these states here will now get input transitions on input A. Is this clear? If anybody has any doubt at this point, please ask before I move ahead, because this is a very important concept and something similar you will use later also when we go from NFA to DFA.
Ma'am, could you explain that part where we are going to the closures, ma'am? I'm a bit unclear about that.
Which part?
Ma'am, the way we are going from epsilon, to the epsilon closures, ma'am. How we are doing that? Like why are we doing that?
Epsilon closure are all those states where you can go without consuming any input. That means following only epsilon paths. And then you consume the input and that is your destination. Okay. So these are the states which will be in epsilon closure. So B is in the epsilon closure of E, and then you consume the input and you find your destination.
Okay.
Okay. Anybody else? So this path, this is not correct. This one has to come at the last. Okay. So if you have this epsilon path, long epsilon path, several let's say several stages, and finally you have an arc on one and you consume that, and this is now your destination state. Okay, is this clear? So what we have basically done is go from an NFA with epsilon transitions to one without epsilon transitions. Okay, so epsilon transitions, as you already know, they add another extra difficult level of non-determinism while working with a finite automata. So we are trying to reduce those non-determinisms. Basically, our target is to get a DFA, because a DFA is good when I'm trying to design a checker. Okay, but NFA makes the task difficult. So now we will try to see that we have removed epsilon transitions. We have an NFA without epsilon transitions. Okay, so usually when we refer to NFAs, by default it means an NFA without epsilon transitions unless otherwise specified. Please remember that. Okay, so now we have to go from NFA to DFA because DFA is our target. Now this is an important result, that for any NFA there is always a corresponding DFA which accepts the same language. Remember, accepting the same language is a very, very important part. It is the accepting of the same language which makes this NFA and DFA, or epsilon NFA and NFA, equivalent. Okay, so that is how equivalence is defined when we are talking of finite automata. Okay, so equivalence means the same language has to be accepted. And what this means is there cannot be even a single string which is accepted by one and rejected by the other. Okay, whichever it is, NFA or DFA. And the proof of this equivalence is usually given in the form of a construction, subset construction. Okay, we'll look at this. At the number of states, please remember, when in the process of removing any kind of non-determinism, we often increase the number of states in the finite automata. Okay, so number of states can be very large in DFA. The NFA could be a very compact representation of the same language. Okay, and because they are equivalent to DFAs, and DFAs already we have seen the language accepted by DFAs, it's called regular language. So NFAs also are accepting regular languages only. So NFA, epsilon NFA, DFA, regular expression, which you will be studying later, all of these express what are called regular languages. And in addition to regular expressions, there is also something called regular grammar. But grammar I will not introduce. Your SD sir will introduce it when he discusses the various language hierarchies. Okay. So the next thing that we have to do is convert an NFA into a DFA. Okay. So what this theorem now, because I told you the TOC is a mathematical subject, so we have to have a mathematical approach to it. So even though we are actually constructing an DFA from an NFA, we are going to put it in theorem form. Okay, so the theorem is the language L is accepted by a DFA if and only if it is accepted by an NFA. And since you have all studied discrete maths, you know that whenever you have any statement with an if and only if, you require to prove it. You require to prove it in two parts. One is for the if part and the other is for the only if part. Only when you prove these two, let's say, equalities or these two statements, then your if and only if statement is proved. Okay. So since this is the theorem, what it says is NFA and DFA are equivalent. That means language accepted by DFA is also accepted by NFA if and only if it is also accepted by an equivalent NFA. So they are equivalent, NFA and DFA. So if part, prove by showing that every NFA can be converted to an equivalent DFA, and only if part, that is the opposite direction. The only if part is actually trivial. That is why nobody talks about this. Every DFA is also a special case of an NFA where each state has exactly one transition. Okay, you can have multiple, but nobody says that you have to have multiple. You could also have one. If you have one for every case, then it is actually a DFA. But a DFA is a special case of an NFA. Therefore, this only if part proof, strictly speaking, we do not need to show. So what we have to do is we have to show that for every NFA, you have an equivalent DFA. And this we will do by constructing a DFA accepting the same language for a given NFA. Okay. So the proof for the if part, a language is accepted by a DFA if it is accepted by an NFA. So rephrasing that, for any given NFA, we can construct a DFA such that the language remains the same. Okay, so how to convert an NFA to a DFA? This is now our big question. So our next discussion is going to be how to convert an NFA to a DFA. Okay, now this we have already seen several times that in NFA, it is possible when you have multiple outgoing arcs that your current state is not just a single state, but a subset of states. Okay, a subset of states. This subset of states concept is very, very important because this is the fundamental basis of your subset construction procedure. Okay, so the idea is to represent each such subset of NFA states. Okay, so suppose I am in a particular state and I have outgoing transitions on an input symbol, say A, and I can possibly end up in 3 or more different states. So this subset of states to which I can end up, this subset of states represents a single state in the DFA, in the equivalent DFA, and we have to find such subsets of states. Okay, so the subset of NFA states can represent a single DFA state. This is the most important or the fundamental idea behind our construction procedure. Okay, so some amount of formal definitions first. So given an NFA, now NFA definition you already know, Q sigma delta n. We use this subscript to show that it is the transition function of the NFA. Okay, Q0 and final state F. So construct an equivalent DFA. Okay, where the set of states is now 2 to the power Q. Now what does this mean, 2 to the power Q? You have just come from DMS, so I expect an answer from you.
Ma'am, total number of subsets, ma'am.
What is it called?
Ma'am, power set.
Yes, very good. Power set. It is the power set. So it is the set of all possible subsets of Q. Okay, starting with the empty subset also. Okay, the empty set is also a subset. So 2 to the power Q is the power set. So what it basically means is the DFA, for in the DFA, the set of states is all possible subsets of the sets of the NFA. Okay, actually, we will not be using all the states, all the subsets. Some of them only are actually used. Okay, the fewer the number of subsets, the smaller the DFA. The input alphabet remains exactly the same. Please note, it cannot possibly change. Okay, why can it not change? Because after all, we are accepting the same strings. Okay, the same strings are made up of the same input characters. So input alphabet remains the same. Logically, it means that. And the start state also remains the same. Only now, remember, it has to be a set. So it is now not just Q0, but it is the set consisting of only the state Q0. Okay, because the sets of the DFA are sets of states of the NFA. Q0 is a set of the NFA. So in the DFA, it has to be a set containing Q0. And the final states are all those subsets in which one of the states is a final state of the NFA. Okay, so something similar to what we just did. If if the epsilon closure contains a final state, then that set that state becomes a final state. Okay, this is something similar. If you are representing a subset in which one of the states is a final state, then this should also be a final state in the DFA. If you are not able to understand now, don't worry, we have examples and you will be able to understand. But as a DFA state, okay, so in the DFA, what happens is, can you hear me?
Yes, ma'am.
Okay.
Yes, ma'am.
So in the DFA, what happens is all these subsets, suppose I could have, for example, a subset consisting of say Q1, Q3, Q4, Q7, where all these Qs are actually sets from the NFA, and this subset now is a set of the is a state of the DFA, but I will not call it a subset. I will give it some other name. Maybe I'll call it QX, okay, or say Q4, or maybe I'll call it A. So this now it is no longer treated as a subset, but it is treated as a single unified set in the DFA. Let's go to the example. The example will make things better. I think here I need to show you the slideshow. Just a minute, please. I think something's messed up. Can you still see my slides?
Yes.
Why it's coming?
Yes, ma'am.
Why
Yes, ma'am.
two of them? Do you see one or do you see two?
I see one, ma'am. It's
One
NFA to
slide.
DFA construction example.
My screen is messed up. Anyway, let me continue as long as you can see it properly. So we are going to do a NFA to DFA construction. The starting NFA, the NFA which we begin with, is the NFA which is shown on the left. You can see it has three states: Q0, Q1, and Q2. Q2 is the final state. And can anybody explain what kind of strings it will accept? It is given here there on top. Okay. So the language L consists of strings W such that the strings end in the suffix 0, 1. Okay. So that tells you that the input alphabet is also 0, 1. Okay. So input alphabet, you can see it is 0, 1. The set of states is Q0, Q1, Q2, and everything else follows. So the transition table is given there. All of you can see the transition table?
Yes, ma'am.
And input, the start state, it is indicated by an incoming arrow. The final state is indicated by the asterisk as before. Okay. And because it is an NFA, some of these table entries are not single states, but sets of states. Okay. So to create a DFA, what do we do? First of all, we enumerate all the possible subsets. Remember this. Can you see the set of subsets now? Do you see any change in the screen?
No, ma'am. No, ma'am.
Okay.
It's just written step 0, enumerate all the possible subsets.
Okay. Now do you see them? Can you see the subsets now?
Yes, ma'am. Yes, ma'am.
Yes, ma'am.
Okay, okay, very good. Then it's working. So all the subsets, these subsets are now going to be the states of the DFA. We are trying to create the DFA. Okay, so what are the subsets? First is the empty set, then all those subsets with single elements, Q0, Q1, Q2, then those subsets with two elements, Q0, Q1, Q0, Q2, Q1, Q2, all possible combinations basically. And then subsets with three elements, which is the largest, which is the complete set. Okay, so this is the power set of big Q for the NFA. Okay, can you see that the power set is there, given there before you? Okay. Next, what do we do next? Determine the transitions. Okay, so determine what are the transitions. Transitions will determine in the form of the table. So this is the table. This table, is it visible to you?
Yes, ma'am.
Okay. So how do these transitions come? So from Q0, for example, you go to Q0, Q1. Can you see that in the DFA table also? You are going from Q0 to Q0, Q1. Similarly, Q0. So these transitions are basically all the sets to which there could be transitions from in the NFA. Like for example, let's take the state Q0, Q1, which is the 5th row. Actually, if I go in slideshow mode, my pen does not work, so I cannot write with the pen. So take the 5th row, Q0, Q1 in the DFA transition table. Can you see that? Okay. So in the NFA, for Q0, on input 0, we go to Q0, Q1. Okay, so let's put Q0, Q1 here. And in the NFA, for state Q1, on input 0, we don't go anywhere. So no new state is added. Okay, so Q0, Q1 remains the same. So this is the set. Okay. So let's take Q0, Q2. Okay, Q0, Q2. In the NFA, for Q0 on input 1, let's take input 1 for a change. Where do we go? We go to the state Q0. Okay, so let's put Q0 here. And in the NFA, for state Q2 on input 1, where do we go? We do not go anywhere. Okay, so Q0 just remains like that. We do not put another state here. Is that clear? So this is the state now for the transition on 1 from Q0, Q2. Okay. Any other example you would like me to work out? Let's take, for example,
if Q0, Q1 goes to 1, so Q0 goes to Q0 only.
Yes, yes. Okay, let's take that. So Q0, Q1. So let's take the state Q0, Q1. Okay, and take the transitions on 1. So state Q0 in the NFA on input 1 goes to Q0. So let's add Q0 here. Okay, and state Q1, which is the second component, on input 1 goes to Q2. Okay, so let's add Q2 here. Right? So Q0, Q2. So this is now the subset to which you will go from Q0, Q1 on input 1. Is that clear? Remember, in NFA, on a particular input, you can go to a subset of states. Okay, so this is the subset. And this subset, then what would happen if you saw a 0, for example? Let's look for this particular subset in the set of states, Q0, Q2. And then on input 0, we would go to Q0, Q1. So basically what we are doing is we are simulating this NFA only in the form of subsets. Is that clear? So we are not adding any transition which was not there in the original NFA. Okay, so these subsets. So for, okay, let's work out this final subset Q0, Q1, Q2. Which would you like to work out? Input 0 or input 1? Let's take input 0. Okay, so Q0. Now from Q0 on input 0, where do I go in the NFA? I go to the subset Q0, Q1. I could go to Q0 also. I could go to Q1 also. So already 2 possible states are there. So Q0, Q1, I add that. Okay, from Q1 on input 0, where do we go? There's no other.
Are you drawing something on the screen, ma'am? Are you drawing something? Are you drawing something on the screen, ma'am?
No, I'm not drawing. I told you in slideshow mode, my pen doesn't work. Okay, but I'm using the pointer. I think you can follow my pointer. Can you see my pointer?
No, ma'am, it's not visible.
Doesn't matter.
Yes, ma'am.
We are discussing.
It's visible.
Okay, if it's visible, that helps. Q0, Q1, Q2, this last subset in the transition function of the DFA. Okay, so for Q0, see these states here in the subsets, these are the states of the NFA. Okay, so from Q0 on input 0, where do we go? We go to Q0 also and we go to Q1 also. We have these 2 possibilities. So same possibilities Q0, Q1 we have put here. From Q1, is there any new state we could go to? No, because this is 5. Similarly for Q2, this is 5. So no new state is being added. Okay, if we take input 1, for example, for Q0, Q1, Q2, okay, from state Q0 in the NFA on input 1, which state do you go to? You go to Q0. Can you see that? Are all of you able to follow what I'm saying? From Q0 in the NFA on input 1, you go to Q0. So Q0 appears here. From from state Q1 in the NFA on input 1, you go to Q2. So add Q2 here. Now let's take Q2. From Q2 on input 1, there's no additional outgoing transition. So no other state is being added. Okay, so that is how Q0, Q2 appears here. So this is now the subset. Okay, so can you understand how the transitions are being added to the DFA table? For every subset, you take each state of the NFA which makes up that subset and then follow the NFA transition table to add the states to the DFA subsets. Okay, destination subset in the DFA table. Okay, so these are all the transitions. Then what do we do? The next stage is to retain only those states which are reachable from the start state Q0. Okay, so if we did that, so if we go from Q0 onwards, from Q0 we are adding Q0, Q1. So Q0, okay, before that I should discuss something else. How do you decide which are the final states of the DFA? Now you will notice in the table, some of these states are marked with star. Now, what is the reason? Somebody please tell me.
Ma'am,
It
because for
includes the
example,
final state in the
Yes,
NFA.
it includes the original final state in the NFA, which is Q2. So notice that all those subsets which have Q2 are marked with star. Okay, if you had more than one final state, that would still be the same. So you have so many different subsets which are now actually final states. Okay, so next go to the next step, the third step. So retain only those states which are reachable from Q0. Okay, so let's start with Q0, which is the initial state. Now this is the initial state of the DFA. So we can go to Q0, Q1. So Q0, Q1 is marked. We can go to Q0. Okay, so Q0 already is there. So Q0, Q1, let's check out next. From Q0, Q1, we can go to Q0, Q1 and Q0, Q2. So these two, Q0, Q2 is also a valid state. Okay, so Q0, Q2 is a valid state. From Q0, Q2, we can go to Q0, Q1 and Q0. But notice that we cannot go out of these three. Okay, there's no way if we start from the start state, we can go to the state Q1, Q2, for example. Okay, so if you follow the reachable states, if you follow the paths, all the possible paths from the start state, that only some of these subsets, okay, which are now the states of the DFA, will actually be ever used. So what we can do is all those states which are not reachable from the start state, they will never appear in any path for any input, valid input string of the language. Okay, so we can remove these states. So what are the states which we remove? First of all, the first, which is about 5, that we remove altogether. Nowhere are we going to 5. Then these rows are being removed. These rows are also being removed. Okay, so we started out with the power set and we find that many of the subsets are never being used. Okay, so all of these transitions are actually never being used. So this gives you a smaller transition table. Okay, so only these transitions actually matter in the DFA. Okay, and if we want to make these subsets look like states and draw the diagram would look like this. So this is now the equivalent DFA, which accepts the same language as the NFA given on the left. Okay, so we have constructed a DFA, equivalent DFA for the NFA. In this particular case, we are lucky that the DFA also has only 3 states, just like the NFA. Of course, it has more transitions, as you can see. Sometimes the number of states of the DFA can be exponential. All of these subsets in the power set could be used. Okay, so you have 2 to the power q, which is exponential. In the worst case, you would end up using all the states and you would have exponential number of states in the DFA. In this case, we happen to be lucky because number of these rows were struck out. So how can we actually be a little more, let's say, intelligent or smart in creating the DFA? So what would be the algorithm? Now, this is the mathematical definition that all the power set of the set of states, all transitions, okay, and then find the DFA. And when you draw the DFA, you find that many of these transitions are never going to be used. Many of these states are not reachable. So what to, if you are a little smarter, what we would do is we would start from the start state and only add those subsets which appear. Okay, other subsets will not bother about. So that is called the lazy creation of sets. Okay, subset construction. So sometimes being lazy is a smart idea. So the same NFA, now we are going to only introduce those states which we actually use. Start with the start state, add the transitions as before. So when you add the transitions, you find that you have added a new subset. Okay. So make this subset a new state of the DFA. Again, add the transitions as before. I hope all of you can understand how the transitions are being added. Have you been able to understand that?
Yes, ma'am.
Okay. So what you basically do is for this subset, for example, Q0, Q1, you look for all the states to which you will go from Q0 in the NFA and add them to the destination for that particular input character. For say for input 0, from Q0, you go to Q0, Q1. So Q0, Q1 appears here. Input 1, you go to Q0. So Q0 appears here. For Q1, on input 1, you go to Q2. So that's why Q2 appears here. Okay. Now, once you have added these transitions, you find that there are two subsets now. Now, Q0, Q1 is a subset which we have already seen, which we have already added to this list. But Q0, Q2 is a new subset which was not there before. So now add this Q0, Q2. Okay, and Q0, Q2 contains Q2, so it also is a final state. When you add the transitions, you find that no new subsets are being added. Okay, so you can stop there at that point because there are no new subsets which you must explore. Okay, so this is a step-by-step addition of subsets. You don't start out with the power set enumerating the entire power set because here it is just 3 states. What if you had started with the NFA with 100 states? Then you would have to have 2 to the power 100 number of states in the subset. But the DFA actually might not require all of them. Okay, so this is a slightly more let's say intelligent way of going about the thing. Okay, so introduce states as you go on a need basis. Okay, draw the automata. It is actually the same as before. So this process, is it now clear to you? What we have done is we have worked out an algorithm of subset creation on a need basis. Okay, so what are the things we have defined? First of all, for the DFA, remember to completely specify the DFA, you need to define 5 things. What are the 5 things? First is the set of states. The set of states is the power set of the NFA. Okay, input alphabet is already defined, doesn't change. Initial state, actually it's the same initial state as before, only now it is expressed in the form of a set. Okay, so final states we have to define and transition function we have to define. Okay, final state, how do we define? All those subsets which have any final state of the given NFA, they are going to be final states in the produced DFA. Okay, and transition functions, how do you define? Again, it is going to be on the basis of the components of the subsets which make up the states of the DFA. Okay, so for example, if you take the subset Q0, Q1, you will have to look at the destination states for Q0, then you will have to look at the destination states for Q1. So each of these components of the subset at a time you will have to see to find what are the states in the NFA to which you might go? What is the which are going to be part of the destination subset? Okay, and that defines the subset to which is going to be your destination subset in the DFA. Okay. So all of these subsets of the states of NFA are actually single states of the DFA. And the transition function is defined in a step-by-step manner so that you do not add extra states which you do not need. Okay, so this is going to be the basic process. So by defining this transition function now, we have completed the definition, completed the entire specification of the DFA which we have to produce. So this is the final DFA. Okay. So now let's look at an algorithm. This is actually the algorithm for subset construction. Now this actually can be applied directly to an NFA with epsilon transitions also. Directly from an NFA with epsilon transition, you can produce a DFA. So today I'm going to stop at this point. Now this algorithm is also widely available. I'll see if I can give you the PPT. I'll mail it to you because we do not have the Moodle page. We'll have it up as soon as possible. Then we'll put it up in Moodle. But meanwhile, I'm going to mail this PPT to you all. Go through this algorithm. In the next class, we will try and work out another example to make this process clear to all of you. So today, what have we covered? We have first converted an epsilon NFA to an NFA without epsilon transitions. Then we have converted an NFA to a DFA. And all of these we have done without changing the language which is being accepted. Okay, so they are all equivalent finite automata. So now you know that all of them basically they mean the same thing. So why do we have so many different things? Anybody have any idea why we have a DFA, then we have an NFA? Sometimes we are also talking about NFA with epsilon transitions. Anybody have any idea?
Ma'am, for optimization purposes?
Optimization is DFA, certainly. Yes, you are absolutely right. But why NFA? I'm not going to introduce anything more. Will not move ahead in the PPT. Yes, why? I didn't hear. Please come again.
Ma'am, NFA probably gives us more versatility, ma'am. For example, since we are being able to go to multiple states at the same time, it probably reduces the time that is required for operation or going to different states.
Actually, if we talk about operations, then DFA is the better options because it is more deterministic. In NFA, we would have to actually do breadth first search. Breadth first search is more difficult than depth first search. You realize that to implement. Okay. But still, an NFA might be useful because, first of all, it is compact. It is more compact than a DFA. Now, let's go to the previous slide. So you have here two finite automata. One is a DFA, the other is an NFA. Which do you think you can read more easily? What do you understand by reading a finite automata? To try and identify what language it accepts, right? So which is more easy to understand?
Ma'am, the NFA.
Yes. Okay. Because it is more intuitive and it is also more compact. Okay. So that is the reason when we are trying to convert a language which we have only the English like description for. Okay. We understand what we have to do. We can maybe express it in English, but how do you express it in the form of finite automata? We might find it easy to create the the NFA. Okay. And then when we are trying to devise a checker for that, it is easier to work with a DFA. So we can always convert this NFA to a DFA and then implement it in the form of a program. Okay. So if you have to write a program, writing a program or the implementation or to create, if you have to create a sequential circuit, then you would always prefer a DFA to an NFA. Okay. So how would you implement an NFA in the form of a hardware circuit? Don't say it's not possible. It is possible, but it's difficult. Okay. But given a DFA, all of you, I hope, can convert it to a hardware circuit which accepts it, right? Can you do that? Please say yes.
Yes, ma'am.
but you're not very convinced, it appears.
Ma'am, I'm a bit confused about this part. If you could like,
Part.
just recap it, like the part where about implementation
Implementation of what?
of the DA of like, can we not implement the NFA? Like, how do we end up implementing the NFA as a hardware system?
Yes, actually it is difficult.